Howdy everyone, and welcome to the second piece of our look at exponential and logarithmic functions. After we covered derivatives last week, after we just introduced the derivatives of e to the x and ln x, and then their chain rule equivalences, their chain rule extensions, we're going to look today at integration. And we're going to take this a little slower than I took derivatives. Derivatives, hopefully, were fairly straightforward for most people. Integration here is a little more of my focus, something we haven't had quite as much practice with as we've had with derivatives, and something where the techniques we need to use are perhaps a little more complex than simply multiplying by the derivative of an exponent or multiplying by the derivative of whatever's in the ln. So here we're going to be looking at integrating exponential functions, and here you see I've written e to the u. That's going to be a hint as to what the main main feeling about this slideshow is going to be, as to what the main technique we're going to be using might involve this particular letter. All right, so let's take a look at our introduction here. We've looked at the derivative of exponential functions. Today we're just going to focus on e to the x. ln x comes up in the next slideshow. ln x comes up in the next online lecture, in the next video lecture. So for now, we're looking at exponentials. So we've already seen that the derivative of e to the x is e to the x. It was this wonderful thing that stayed invariant under the derivative. It just sat there. So now we instead need to focus on the integral. But the integral is, as we've seen plenty of times before, as I've stated plenty before, it's the opposite of the derivative. The fundamental theorem of calculus essentially says that the derivative and the integral are opposites, that the integral exists as an antiderivative. That's actually how it's defined. So what we have here is we have something where we say, well, if I need the opposite of something that doesn't change, then the opposite also shouldn't change. So here, what we have is if the derivative of e to the x is e to the x, then it stands to reason that the integral, which simply goes, if the derivative is going in this direction, the integral simply goes in this direction. Well, it stands to reason that the integral of e to the x would stay invariant as well. So the integral of e to the x is e to the x plus c. Yeah, remember your plus c's. Don't lose that. So great. Sounds easy. Seems really nice, right? And in point of fact, it is really nice. If we can ever put an integral into this form, we're pretty much already done, right? You just kind of get rid of the integral sign, tack on a plus c, and move on with life. But we saw that with the derivative of e to the x, there's always a but, isn't there? We saw that with the derivative of e to the x, when it wasn't e to the x, when it was e to some function, we had to respect the chain rule. So that means with the integral, we need to undo the chain rule. And our idea of undoing the chain rule was to use u substitution. So yeah, the integral e to the x dx is e to the x plus c, but what if it's more complex? And let's take a look at something that's barely more complex. So let's say the integral of e to the 3x dx. So here's where we're going to revise our definition. And instead of saying the integral of e to the x dx is e to the x plus c, we're going to say the integral of e to the u du is e to the u plus c. Now, all I've done here is replace the x with a u and be like, wow, amazing. But what this is telling us is that the exponential function, e to the whatever, is a prime candidate for u substitution. And we can see where the u is. The place where we're going to be substituting is in the exponent. So our first impulse, and this is impulse one of u substitutions. When you're working with u sub and you actually have an exponential in there, this will be the very first thing you look at, guaranteed. Impulse one is if there's an e and it's got an exponent, we substitute whatever's in the exponent. So let's take a look at that first example, the integral of e to the 3x dx. So here, we need our integrand, the thing in the integral sign, right? This bit. We need this integrand. Instead of being e to the 3x dx, we want it to be e to the u du. So our prime candidate for substitution, the exponent of e, well, let's make our sub. U equals 3x. So if u equals 3x, we follow the same rules of u substitution that we've always followed. So take the derivative of both sides. U equals 3x becomes du dx equals 3. We move the dx over, du equals 3 dx, and then we solve for dx. Dx equals du over 3. So now we can replace dx with du over 3. We can replace 3x with u, and we get e to the u times du over 3 as our integrand. Pulling the 1/3 out of the integral, again, it's a constant, right? Division by 3 is the same as multiplication by 1/3. So it's a constant multiple. You can just ignore it for the purposes of integration. So we just kind of pull it out. We end up with 1/3 times the integral of e to the u du, which, as we saw from our last slide, is that definition we wanted to reach. So the integral of e to the u du is e to the u plus c. So 1/3, the integral of e to the u du is 1/3 e to the u plus c. You could say that this plus c also has a 1/3 attached to it, but it's an arbitrary constant. An arbitrary constant times 1/3 is still an arbitrary constant. So it doesn't matter. We just, the c just eats the 1/3 and sits there. Like, it's just kind of a way to say, hey, that's an extra constant. So don't worry about multiplying c by anything, or adding or subtracting things from c, or dividing anything, or dividing c by anything. It doesn't matter. It's still c. So anyway, going back to this, we end up with 1/3 e to the u plus c. Well, now our last step in the u substitution comes up. We just need to substitute back into x, because we want our answer to be in terms of x, because that's what we started with. So substituting 3x back in, we get e to the 3x over 3 plus c. And that's it. This is u substitution in almost its purest form. It's the place you're going to make your substitution is always the exponent. It's always going to be obvious what your choice is, or should be anyway. And it's always going to be something where you just need to make sure that things cancel down, so that you only have u's left. And we'll see, more complex substitutions in a few more examples that I've prepared. But this is it, right? There's nothing more to be done. So let's take a look at another example. So here, as I said, a more complex example. We've got, let's deal with the integral of 5x squared e to the 3x cubed minus 2, all in the exponent, dx. So once again, first impulse, u is whatever's in the exponent of e. So here, that's 3x cubed minus 2. So follow the same rules. U equals 3x cubed minus 2. Great. Take the derivative of both sides. You get du dx equals 9x squared. And then we go through that same process of isolating dx so that we can replace it with du over something. So we get dx equals du over 9x squared if you've gone through the algebra. So what we end up getting here is 5x squared times e to the u times du over 9x squared, which is right here. So there's some nice cancellation that happens. X squared cancels with x squared, nifty. And that means that we get 5 over 9 e to the u du. I've seen a couple of people in the class, when they try to cancel this, go 5x squared over 9x squared equals 1 over 4x squared. That's not how that works. You're confusing canceling with addition and subtraction of like terms. Be careful about that. Like bases with the same exponents cancel, right? You cancel like bases. You don't add and subtract anything but exponents. And here, the exponents we're adding and subtracting is pretty much just 2 from 2, right? So they just cancel. So don't make that mistake. It's a silly one to be making. You know, especially as a college level student, you don't want to be making that mistake. That one hurts. So anyway, yeah, back to this. So 5x squared over 9x squared just cancels to 5/9. So we get 5/9 e to the u du. Once again, 5/9, just a constant coefficient. In the same way that constants do nothing under derivatives, they just sit there. They're just coefficients. They do nothing under integration. So a coefficient just sits there. So integral of 5/9 e to the u du is 5/9 e to the u plus c. And once again, our remaining step is just to plug back in. We finished the integral. Notice the integral sign is gone, right? We took the integral. Really easy to get confused with exponents with exponentials, by the way. Really easy to be unsure whether or not you've actually taken the integral because it doesn't change, right? So be careful about that. Keep track of your steps. But anyway, back to this. We've got 5/9 e to the u plus c. Our integral's done. So we just need to plug back in our original function for u. We need to undo our original substitution. So 5/9 e to the 3x cubed minus 2 plus c. Job done. And this is it, right? This is all there is to what we're doing. There is nothing more we need to deal with. There's no further. There is actually a further simplification. I shouldn't say there's no further simplification. There is. One of the exponential rules that I haven't really gone into detail about here, because I'm not going to be too bent out of shape if you're not using it, is when you have something like this, e to the 3x cubed minus 2, this is the same thing as e to the 3x cubed times e to the negative 2, or e to the 3x cubed over e squared. Essentially, the idea being that something like x to the a plus b is equal to x to the a times x to the b. I'll just quickly show this here. If you have something like this, x to the a plus b, it's equal to x to the a times x to the b. Similarly, x to the a minus b is equal to x to the a. That's got to be an a. There we go. Over x to the b. For what we're doing in this class, this isn't really going to come up, or this isn't really going to be a major cause for concern for me. I don't need to see the simplification there. I don't need to not see it. If you want to do it, great, go for it. But it doesn't really matter. Really not the point of what we're doing. So yeah, again, this could be rewritten in a different way, but this is more than sufficient. It's not even like a you don't need to simplify type of thing. Like, this is a completely reasonable, wonderful, correct, complete answer. So yeah. If you're not sure what I was talking about with that exponential stuff, it doesn't hurt to know. I mean, it's helpful rules to know, but not really the point of this. Not really the point of this particular topic, and not really something to dwell upon. So if you really feel like it, you can just kind of ignore the last 2 minutes of this particular video. All right. So the other thing I want to look at is I want to look at what happens when we've got boundaries. What happens when our integral looks, you know, has boundary values, looks like this. So really nothing special. As with any other integral with boundaries, we just do the integral as normal and just plug in the boundaries at the end. You get rid of the plus c because that's we're not talking about the same thing anymore. We're not talking about a position on a graph where we're talking about an area under a curve now, so it's a different thing. We know where the graph is. So no need for the plus c anymore, but instead now you need to do that same idea of evaluate the top and the bottom and subtract the bottom evaluation from the top. Really nothing's changed. So for example here, the integral from 4 to 7 of e to the x dx is just e to the x, which is the result of the integral, right? Integral of e to the x is e to the x. It's e to the x evaluated from 4 to 7. So that's e to the 7th minus e to the 4th, which is not, for the record, e to the 3rd. Those two numbers need to be computed individually. I haven't taken the time to do so. It is less accurate for me to compute that than for me to simply leave it as e to the 7th minus e to the 4th. If you wanted to be really fancy, you could rewrite this as e to the 4th times e cubed minus 1, and then you're really, you're really kind of straining, like trying to be as factor friendly as possible here. But I don't care. This is not the type of thing that anyone cares about. So this is fine. E to the 7th minus e to the 4th, completely reasonable answer. A textbook answer, again, would be something like e to the 4th times e cubed minus 1. But meh, that's oversimplification as far as I care. So yeah, let's just take a look at an example here. So here we've got evaluate the integral from 0 to 3 of 4x minus 2 times e to the x squared minus x dx. So we're going to do a u sub. We're going to leave the boundaries alone. We're going to leave the boundary, in other words, we're leaving the boundaries in terms of x. I've kind of, in this class, I've kind of gone back and forth with sometimes switching the boundaries over to u so we don't have to flip back, and then sometimes leaving them in x. For my examples, at least, I'm just going to leave them in x, and we'll flip back just to be more consistent. So let's take a look at the substitution we choose to do. So once again, even though this is a more complex integral, right? Maybe if you're not really sure what's going on yet, it might be unclear what your substitution is. Once you're kind of seeing more of these, it shouldn't be unclear. The substitution is whatever's in the exponent of e, every time, never not. For the purposes of when we're just dealing with exponential functions like this, this is your first impulse. It might not always work when you have more complex integrals. You might need to be more creative than that. But for Calc 1, you won't be. You won't need to be more creative. You won't need to go above and beyond that. So whatever's in the exponent of e, that's a good choice. So you can't see it because I don't have my camera trained on me. I've got it trained on the slideshow, but I was giving a thumbs up. All right, so so here we've got u equals x squared minus x. That's in the exponent, right, of e. So again, same rules of u substitution. We've chosen our u. We take the derivative in order to try and isolate dx. We get du dx equals 2x minus 1, which is going to eventually yield dx equals du over 2x minus 1. So we plug this stuff in. We plug in u equals x squared minus x. We plug in dx equals du over 2x minus 1. And then factoring that 4x minus 2 into 2 times 2x minus 1. Remember, factoring is your friend, right? It's going to help you make sure that things cancel when they should. It's going to help you not make, arithmetic or not make algebraic mistakes. So we end up getting 2 times 2x minus 1 times e to the u times du over 2x minus 1. So those 2x minus 1s cancel, and we get the integral from 0 to 3 of 2e to the u du, which is just going to go to 2e to the u, evaluated from 0 to 3. Those boundaries are in x, so we need to sub back before we plug anything in. So we get 2e to the x squared minus x, putting back the original substitution, evaluated from 0 to 3. And now we just plug in those numbers. And here's another one where I've seen a lot of people make mistakes. Plugging in this 0 does not mean your answer is 0. It means you're plugging in 0 for x. So here we get 2e to the 3 squared minus 3, which is 9 minus 3, which is 6. So 2e to the 6th minus, and now the evaluation of the bottom boundary. 2 times e to the 0 minus 0. That's 2e to the 0. E to the 0 isn't 0, it's 1, right? Any non-zero constant to the 0th power is 1. So we end up with 2 times e to the 6th minus 1 is our final answer, all factored out. I don't care if you leave this as 2 times e to the 6th minus 2. Please don't leave e to the 0. I said I don't mind not fully simplifying, but that one hurts my soul. Please don't leave something to the 0th power. It's 1. Make it 1. We'll see another one where I'm going to kind of be upset if something's left unsimplified with logs too. Namely, when we get there, log of 1. Log of 1 is always 0. Please don't write log of 1. It hurts. So yeah, anyway, other than making sure that you write, that you get rid of the e to the 0 and just make it a 1, this problem's done. Again, this is as simplified as it's going to get. You could actually calculate e to the 6th, but you're actually going to make your answer less accurate by doing that, because now you've got a decimal, and e is an irrational number. It cannot be written with a closed decimal, or it cannot be written with a finite decimal, rather. So, by trying to compute this, you make your answer less accurate. So don't. 2 times e to the 6 minus 1. This is a great answer. This is the best answer. There is no better answer than this. So yeah. Let's take a look at a couple more examples I've prepared, and that'll wrap it up. So flipping back to the whiteboard. There we go. Let's take a look at something where we've got a need to both factor, and we've got one of those annoying things where some of our integral is substituted, and where some of our integral needs a substitution and some doesn't. So, let's take a look at this. The integral of 3x to the 4th minus 3 times e to the x to the 5th. That is the worst 5 anyone's ever drawn. Not actually better. There we go. All right. 3x to the 4th minus 3 times e to the x to the 5th minus 5x. This is all in the exponent, plus 7x. So here, notice this 7x is not part of the exponent, right? It's just its own term in the integrand. So what we're going to do is come back, please. This whiteboard sometimes does this. Give it a sec. There we go. So what we're going to do is we're going to deal with this part of the integral right now. This part we just integrate on its own, right? Integral of 7x dx is just going to be 7x squared over 2. And we're just done. Like this is all that we have to do with that 7x. There's nothing more to be done there. So that's its own separate integral. We've gotten it out of the way immediately, so neat, done. Okay, this 7x doesn't matter anymore. Let's focus on this now. So here again, we want to make a substitution, and our choice for substitution here is whatever's in the exponent of e. So that means our u should be x to the 5th. I regret using 5. Minus 5x. That means that we get that du dx is equal to 5x to the fourth minus 5. That's a 4. And what this is going to end up giving us is that dx is going to be equal to du over 5x to the fourth minus 5. And let's let's try this again with less terrible drawing. Neat, better. Okay. So this gives us that dx equals du over 5x to the fourth minus 5. So our new integral becomes, and notice here that I'm going to factor 3 times x to the fourth minus 1 e to the u times du over 5 times x to the fourth minus 1. And now we get this nice cancels. So we get the integral of 3/5 e to the u, that's an e, du, which is just, try that again, 3/5 e to the u. And again, we've got a plus c here. It doesn't really matter which plus c I'm using, or both. You could be like C1, C2, whatever, if you want subscripts. It really doesn't matter, because the point is that ultimately we're just going to add them together, and an arbitrary constant plus another arbitrary constant is an arbitrary constant. So just call it C and move on. So here, our last step is just to put our substitution back. Put this bit back. So here, what we end up getting is 3/5 e to the x to the fifth minus 5x. That's a minus, plus 7x squared over 2 plus c. And there's our answer. Job done. So notice this 7x squared over 2, this 7x became 7x squared over 2. That just happened separately, right? We just don't even try and include this as part of the u substitution. Just do it on its own. If you've got a piece of the integral you can do immediately, do it immediately. Don't try and kind of incorporate this into the u substitution, because it's just gonna make your life worse. It's doable, but only if you're doing some very clever algebra and then needing to make another substitution to fix it. Better just to do it on its own and just complete the simple integral. So yeah, this is it. I mean, the main body of what we look at here is this part, right? We make the substitution of what's in the exponent. We do u sub in the normal way, cancel where we need to cancel, and you've got your answer. So let's go ahead and move on to one final example here. I'm going to go ahead and clear the board. So we will go ahead and try an example that's got some boundaries. So let's take a look at the integral from 0 to 3 of 6x squared minus 4. Why? Try this again without the additional information here. So again, integral from 0 to 3, 6x squared minus 4. Let's try it this time. And we'll do times e to the x cubed minus 2x dx. So let's go ahead and that's got to be a parenthesis here. There we go. So let's go ahead and try and solve this. So once again, we want to pick what our substitution is going to be, right? And our substitution is always going to be whatever's in the exponent of e. So u is equal to x cubed minus 2x. So what we're going to do here is just go ahead and take the derivative of both sides. Du dx is equal to 3x squared minus 2x, or minus 2 rather. So we get du dx is equal to 3x squared minus 2. That is just a miserable d. All right. So now once again, what we'll do is go ahead and turn this into an isolation for dx. There's plenty of other ways to go about making these substitutions, but in my opinion, this is algebraically at least the simplest. So we're gonna kind of stick with this idea. So dx is going to be equal to du over 3x squared minus 2. And here we want to see if this is going to cancel. So one of the things we might want to do is, once again, we can try and factor things out of this. So this, this right here, for the record, can be factored into 2 times 3x squared. Whoa, there we go. Minus 2. So that's good news, because 3x squared minus 2, 3x squared minus 2, these are going to cancel. So that's good news. So yeah, let's go ahead and actually put this away. Let's go ahead and put this integral away here. So again, we're leaving the boundaries in x. We'll deal with those later once the integral is done. So we get 2 times 3x squared minus 2. And then we'll just go ahead and get e to the u times du over 3x squared minus 2. And here, what's going to happen is these things will cancel. So we end up getting the integral from 0 to 3 of 2 e to the u du. So, pretty simple integral this. What we end up getting here is just 2e to the u evaluated in x. So we'll need to switch back to x before actually completing the evaluation, but the integral here, pretty direct. Once again, the moment we've hit this kind of coefficient times e to the u du, we're pretty much done, right? There's nothing special here to be done. The integral of e to the u du is easy. It's just e to the u. So we go ahead, we put the original equation back. So we get 2 e to the, and it was x cubed minus 2x. And we evaluate from 0 to 3. And this is going to be 2 times e to the 27th minus 6. So that's 2e to the 21st. Minus 2e to the 0. And just like the last problem, it's nice to factor out that 2, and it's nice to turn that e to the 0 into a 1. So we get 2 times e to the 21st minus 1. And I make that out to be in and around 2.6 billion. So, kind of better to leave it like this. I don't really want to write out 2.6 billion if I don't have to. So let's just leave it like e to the 21st minus 1 all times 2. That seems great. Neat. Final answer. So yeah, a lot of what we need to do for integrating exponential functions like this, for integrating e to the whatever, is just to make a u substitution where your u is the exponent. And that's really, the takeaway from this. That's really all you need to be focusing on. That's really the main point here. So yeah, that's it for now. Thanks, and until next time.